There's a seat here. Okay, I think we can just get started. Today we have Anna. Anna got her PhD in Cancer Science from yeah, University. Yeah, I tried. And then she became a postdoc within CGD Ocean section starting 2021, and then she has been working on a wide range of different topics, such as pre-field campaign for the tropical Pacific observing system process study, and we're also estimating diabatic and adiabatic upwelling from ocean-state estimates, as well as marine waves. So today, she's going to give us a talk about the tropical Pacific variability from both models and observations.
Thanks. Yeah, I lied.
Yes, and she will be starting a new journey to be a professor at the University of Livermore starting September.
Yes, Liverpool. Thank you. Liverpool. Yeah. And I did start in 2019, but that was before the pandemic, so who knows what happened. Okay, and thanks for coming. Thanks for being online. Thanks for being here in this room. I was really ready to talk about tropical Pacific variability, which is something I've done before, and I know everyone remembers every word that I say, so I figured I'll talk about something else today. I was going to give you a little bit of an overview of my research journey and my plans and what I've done here and even what I've done before, because when I arrived here during my PhD, I was working in the tropical Atlantic. And then I arrived here, I was still finishing up that work. And then I was to the seminar, but then the pandemic happened. So I never talked about any of that. So this is going to be a blast from the past. Then I'm going to talk a little bit about my move here and to the big brother ocean, the Pacific, and my work that I've done here. And I'm also going to talk about a couple of things that I never got to finish so far that I'm going to keep working on and do in the future. Talk a little bit about model biases, how to look at model biases in this region, and more upwelling stuff, because that's sort of my main focus, tropical upwelling airs interactions, and a little bit about future plans, which exactly I'm doing to the University of Liverpool. And I'm just trying to figure, can we turn the volume down? Is that possible?
Yeah, I will try.
Thank you. Yeah, I'm sorry, it's just, I really appreciate everyone joining online, but there's a bing every time, so I'm distracted. Okay, so let's start with the tropical Atlantic. Again, the work that I never really got to talk about. And so we can ask ourselves the questions, what is the main pattern of air-sea coupling in the tropical Atlantic? Which looks like something you might recognize or might recognize from work that I've talked about in the past in the tropical Pacific. So in the tropical Atlantic, we have a cold tongue, much like the Pacific. There's a mean zonal sea surface temperature gradient, and the standard deviation of this pattern is also very much similar to what it looked like in the tropical Pacific. So we have the warming of the cold tongue or a cooling of the cold tongue on interannual time scales that is impacted or impacts the circulation, the oceanic and the atmospheric circulation. So we have the zonal temperature gradient. Sometimes the cool temperatures aren't quite as cool, they're a little bit warmer, which leads to a reduction in the zonal surface winds, which then triggers Kelvin waves in the western tropical Atlantic, which communicates a deepening of the thermocline in the east. And then there's a deeper layer of warm sea surface temperatures, which again makes the eastern part, which is usually colder, less cold or warmer. And that's called the Birke's feedback. And that's what this is kind of why I thought I had a right to study the tropical Pacific, because I've been doing this in the tropical Atlantic. And so something that I looked at during my PhD was the parts of this Birke's feedback in the tropical Atlantic, because the tropical Atlantic is a little more I'm going to say this wrong, but it's a little bit more complicated than the tropical Pacific because there's lots of influence on the lands, and the modes of variability are not quite as well separated, so it's not quite as dominant. The one mode of variability, this Atlantic Nino, isn't quite as dominant. So there's influences of other modes of variability on the sea surface temperature. So I wanted to quantify how important and how prevalent the Bjerknes feedback in the tropical Atlantic is. And at that time, ERA interim was the latest thing. So we looked at that. And the way I analyzed this was doing correlations between sea surface temperature anomalies in the east, in this box that I've indicated there, on the tropical Atlantic wind stress, zonal wind stress. And so that's the first part of this feedback, where the sea surface temperature in the east mediates the zonal temperature gradient, which mediates the wind stress and has a signature in the western tropical Atlantic. And so I was interested in, so I was really new to climate science. I'd actually done theoretical chemistry before I came here, and people had these set seasonalities of these things and said, you know, that always happens in June, July, August. And I was just really curious to see, like, you know, how can I see this from my own analysis? So I looked in May, which is one of the predominant modes where the Bjerknes feedback is active. And then I also looked at the signature of the sea surface temperature anomaly in the east on wind stress in the other month for the seasonal cycle. And so basically wherever there's a large red blob means there's large correlation between the sea surface temperature and the zonal wind stress. And so from my analysis, it didn't really look like June, July, August was the main effect. So it looks more like May is really the predominant beginning, where you can see very strong impact of sea surface temperature anomaly on wind stress anomalies in the Western Tropical Pacific. And then you can see kind of this interesting movement. The Bjerknes feedback is really an equatorially locked mechanism because it depends or relies on the equatorial locked Kelvin waves that closes the feedback loop. So the wave that brings the anomaly from the west to the east along the equator, along the waveguide. So it is relevant where we have this correlation. And so you can see that you have some modulation of wind stress almost throughout the entire seasonal cycle, except for February. But then it moves sort of off equatorially, which is related to where the tropical intertropical convergence zone is located at that region. So that sort of background state modulates the response of the wind stress to a sea surface temperature anomaly. And so I looked at this in ERA interim, but you know, the tropical Atlantic community already knew that there is this Bjerknes feedback happening, and it's modulating the sea surface temperature variability in the tropical Atlantic. And something that we really wanted to know is how well do CMIP models simulate this? And one of the reasons for us to be interested in that, and I don't have a picture here, but is there's a really big sea surface temperature bias in the tropical Atlantic along the equatorial region. The sea surface temperatures are too warm, which is kind of a plot twist. Then I came here and everything in the Pacific is too cold. So it turns out I didn't know everything. So in order to compare how the CMIP models did, and I wanted to look at sort of like the model ensemble, all the models in the CMIP ensemble, I came up with this model reanalysis agreement metric, which is a pattern correlation. So I call this MRA. It's a pattern correlation between the pattern that you see in ERA interim and the pattern that you see of the correlation between the sea surface temperature and the wind stress that you see in the models. And then I have also the correlation strength between the sea surface temperature anomaly and the wind stress in the box where it's relevant for the Bjerknes feedback. Again, this equatorially locked box. And the reanalysis value is in red here, and the multi-model mean, sort of ensemble mean, is in pink. So this gave me some idea of how well do the models do, because if you had a perfect model, it would sit where the star is right there. It would have a perfect pattern, like pattern correlation agreement, which obviously you cannot really expect that because there's other data at play, but you would get close.
What months or what are you using for this?
Give me 1 second. Thank you. Very relevant question. It's going to be there. So, so to answer this quickly is most of these, so the first part of the Bjerknes feedback, the sea surface temperature on the zonal wind stress, is assumed to be a pretty much immediate reaction. So you have a 0 lag correlation. Later on, there's going to be a lag correlation. And I looked at this for different months. The different months that I found were relevant in my house before. Anyway, so basically the perfect model would sit sort of up there on the right with this as strong correlation as the reanalysis and with the same pattern as the reanalysis. So I did look at this for May, June, and July, which were the months that May was the one that I found this to be the strongest, and June, July, August. I neglected August because I didn't find in my analysis before that was a very dominant month. Maybe if you average June and July, dominate, which is why you would see this signal as well. But again, I was a young PhD student and I was very, what's the accurate, word to say for anal? I wanted to find out exactly when is this mechanism happening and when is it represented. So I split it up into May, June, July and didn't do the seasonal variability. Okay, so you can see a spread that sort of gets better as you move throughout the seasonal cycle, which again could be related to the representation of the ITCZ, which allows for this zonal winds to react to the temperature gradient. But that's something that at the time I wanted to pursue further in the future and haven't until now. So this is at the same time also something I will be looking into again. And then I did the same analysis for the different parts of the Bjerknes feedback. So the upper row was the first one, the sea surface temperature anomaly in the east on the wind stress, and then you get the wind stress on the thermocline depth. So this is basically the Kelvin wave that propagates the anomaly from the west, from the wind stress to the east, which actually looks really good. So it seems that most of the ocean models create this accurate response of wind stress forcing in the west, in the east, right? And then the last one is how then does the depth of the thermocline impact sea surface temperature? And this is something that maybe people sort of couple them because you have a deeper mixed layer, so a deeper thermocline, deeper warm water, so more sea surface temperature. Which we observe in the real world, but the models honestly are not quite as great. So I want to know how well are these Bjerknes feedback parts represented. Again, the Kelvin wave one looks really good. The one where the wind stress reacts to the sea surface temperature gradient, I put a shrug there because the first one doesn't look so great. By July, we're kind of looking okay. We have some resemblance, so we can say, okay, maybe this pattern correlation, maybe the strength is actually really close. Maybe the pattern is a little bit different, but we have this mechanism represented. So the atmosphere reacts to the sea surface temperature forcing. But then if you look at the lower one, that was something that's really weird to me because I just started kind of saying that already, that it's really something intuitive to oceanographers when you say you have a deeper mixed layer, so you have more heat content, so you have warmer sea surface temperatures. That's something that everyone has in their minds that's, like going together. And that is the one that's not working so well, even though it's the local vertical response. So that was kind of like, okay, what is happening here? So I was curious and I wanted to see what's going on below the surface. So the next step that I did is I correlated these eastern sea surface temperature anomalies, so they would be here, with subsurface temperature anomalies. So you can kind of see, and this is a 0 lag correlation. I did this with lags where you can see the Kelvin waves, just showing you this one. The one figure, the results do not change if you introduce a lag. But so you're looking now at the depth of the ocean along the equator, and you can see that there's really this equatorial waveguide along the thermocline that influences the sea surface temperatures in the east. So a change in thermocline depth is really this adjustment that we get from the Kelvin wave. And if we now compare this figure to the different models, you can kind of see where the confusion is coming from or where the lack of skill is coming from. So we have some models that actually look pretty good, and I'm just putting the numbers here. Actually, I probably should have looked at which one is CSM, but I didn't do that. So I'll go back and find out which one.
The best one.
Absolutely, yes. Let's just go with that. Yeah, but you can also see, there's something really weird sort of happening here with the disconnect. There's something where this would probably be the idea. I mean, we're going really deep here, just down to 300 meters, which is too deep, but this is sort of this idea that when you have more warm water, so the thermocline is deeper, then the sea surface temperature is warmer. That's kind of analogous with this understanding. But there's a lot of models that don't have this. And what is happening here? So I was curious, this is kind of how I got from climate science to the ocean, because I was like, what is going on with the ocean? And something that I was then able to use is I had helped develop a single column model, a coupled ocean atmosphere single column model, that we could put in the ocean and study the vertical processes. And that seemed relevant here because this connection of the subsurface to surface is this vertical process in the ocean. So I had some fun playing around with this single column model. And so what I did is I used a mooring observation. So this, you can see the climatological seasonal cycle here. See this really rapid cooling, and this cooling is where you would expect maybe sea surface temperature and subsurface temperature to be coupled strongly. Like it's a really big change. What is happening here in the processes that drives this change? And in dots, you can see 3D EC Earth. So just to compare, is there something? Does our single column model do sort of a similar thing? So I just zoomed in on this short time period here where we have the strong cooling, and I simulated this period with the forcing obtained from the mooring data with the single column model. And you can see a similar structure to the 3D. Basically, it stays too warm, it doesn't get cool enough, and Pirata is the mooring observation. So we retain this warm bias from the single column model. So now, because it's a single column model, you can run a bunch of experiments really easily. And one thing that I was interested in, I did a bunch of experiments with the atmosphere and changing atmospheric forcing as well. I'm not showing you those because they didn't make the biggest difference. But what we did here, so in this case, I looked at the vertical mixing parameterization in the single column model, which was the same as EC Earth NEMO, that model that I used before and we changed some of the parameters, for example, laminar turbulence input, and we changed the stratification n square to see whether we are just not, because the models usually have a too diffuse thermocline, so maybe something in the stratification there is telling the mixing parameterization that it doesn't create the right mixing. But even if we deviate the accurate profile, it didn't get much better. But something that did make a big difference is the vertical mixing efficiency coefficient in the turbulent kinetic energy vertical mixing parameterization. And that is something that I've had a lot of, now that I'm talking more to observationalists and having a lot of discussions about this, because there's a range that this mixing efficiency can take. It's usually sort of accepted to be 0.2, but it really could be a bigger range. And then depending on whether you're an observationalist, you work very hard to get this range. And then we climate modelers say, well, actually, if you change this range, it really matters a lot. And I can get a really good representation of the seasonal cycle or the change in sea surface temperature if I change this mixing efficiency. So that kind of got me interested in mixing processes. Okay, so then there was a paper that vertical mixing is deficient in this specific parameterization in the single column model. We translated that to the global climate model and we ran with the changed mixing coefficient and did get a better representation of the Atlantic, the tropical Atlantic, not everywhere else, because you can't just change something and then, make everything better. But that is kind of what, again, got me interested in coming here to a model development center, learning more about how these, how that works and how you get the model to potentially be better. Again, being a young naive postdoc in 2019, thinking that, okay, now, we're going to go. And then the other thing that brought me here was the Europe observations, because Frank, together with Llewellyn Thompson and Billy Kessler in Seattle, had a project that was a pre-field campaign for going out and measuring. So taking measurements of processes such as the ones that are relevant in the tropical Atlantic, but now in the Pacific. And the opportunity to co-design this field campaign. So that was something that I was really excited about because, especially when I started getting into the, changing of the mixing coefficients, I was kind of my own little person, changing the knobs within the ranges I could find. But I guess, there was, I can find in the literature, but there was, also a clear need for more observational guidance for this. So at that point, there was a couple of pre-field pilot studies going on that I'm just showing some pictures on the right, where people have started testing new observational methods to go and take these observations, and an idea to extend the tropical Pacific observing system, which is kind of shown here, where on the equator, where we have strong shear, which strongly impacts the mixing, where we can get more observations about the variability of the system, about the processes in the system. And so that was something that was really exciting to me. So I came here as a postdoc to study the scales, variability, and processes in the near surface Eastern Equatorial Pacific in support of this tropical Pacific observing system. And so now, just to show you that there was this word scales in there, and the word scales is in there because the tropical Pacific, and I'm now talking about the tropical Pacific, but honestly, I could be having a similar conversation about the Atlantic, because again, most of these processes that are active in one basin are also active in the other basin, maybe with different ratios of how dominant they are, right? So I'm going to come back to that in a little bit. But yeah, so on the scale interactions here for the tropical Pacific, I mean, this was the sea surface temperature anomaly of last November, where we were having this big El Nino that you can see. So there's this basin-wide El Nino scale oscillation, and if we swap from sea surface temperature anomalies to now sea surface temperatures, you could see even during this El Nino southern oscillations, the warm phase, there were these wave patterns in the tropical Pacific present, which are the tropical instability vortices or tropical instability waves. And if we zoom in on, so they're on much smaller scale, right, than the basin scale El Nino southern oscillation. If we zoom in on one of these vortices, you can see the processes that are modified by the passing of these vortices, which is, among other things, turbulent mixing, which again I was interested in before already, which happens, on very small time scales. And the really cool, interesting thing is that these really small processes that are modulated by the medium small processes, like the tropical instability waves, then feed back on how the El Nino southern oscillation develops and how the large scale develops. So that's some of the scales that I've been focusing on since coming here. And so this is something that I usually kind of start with, and now I wanted to bring that in now. The Equatorial Pacific region, I just mentioned it, is a really strong upwelling region. So everyone has, I think, heard of equatorial upwelling, sort of partially driven by the winds and divergence. And so then there's cold water supplied from below. In the Equatorial Pacific, the other thing that we have, and in the Atlantic to some extent too, is we have current shear between an easterly wind-driven westward surface current in the mixed layer, the south equatorial current, and the equatorial undercurrent that flows along the thermocline towards the east. So there's these two currents that are lying on top of each other, and they are opposing each other, which leads to this really strong shear, which leads to mixing, indicated here by all these little swirls, which can communicate heat and properties, so it can take up heat into the ocean and communicate properties such as oxygen, etc., from the lower ocean to the surface. And so that is one of the reasons why this region, if you're interested in mixing processes and also testing maybe mixing parametrizations and improving mixing parametrizations, is really relevant, because you have this strongly shear-driven regime, so which means that mixing is going to be present. But you also have a lot of variability, because if you have an El Nino, these shears are going to be much weaker, during a La Nina much stronger, and they're also modulated again by these tropical instability waves coming by. So you can see lots of regimes sort of going by focusing on this specific region. So before I joined in this tropical Pacific observing system, people had, of course, been thinking about that for a really long time. And part of the processes that they were thinking about was something called PUMP, Pacific Upwelling and Mixing Physics, which was one of the studies that was highlighted in, as a target for this pre-field campaigns, to figure out and understand more about Pacific upwelling and mixing. And so an analysis or a framework that we came up with is this water mass transformation framework that actually unifies mixing and upwelling and shows you how much mixing contributes to upwelling and how much of this mixing driven upwelling is part of the total upwelling, which is partially again also driven by the winds and the divergence on the equator. So now we're not looking along the equator anymore, we're looking sort of across the equator. So we still have the equatorial undercurrent along the thermocline, but now it's sort of going, now I have to think, if this is no, I can't do it. It's out or into the, so it's going sort of towards us and not along. And so you see, I neglected to put in the south equatorial current, but still the equatorial undercurrent is going to be much stronger in the center than it is at the edges. And again, then you have an opposing overlying current, so strong current shear that results in mixing. And this is also the region where you have this equatorial upwelling. And so this mixing gives rise to a turbulent heat flux, which brings heat into the ocean. If you take the divergence of this turbulent heat flux, then you get the heat that is deposited at each location. So basically, if there's turbulent heat flux, but you need to look at the divergence if you want to know what it does to this layer in the ocean. So if the divergence is negative, it's going to be taking up heat. And if the divergence is positive, it's going to be depositing heat into the ocean. So this turbulent mixing takes heat from the surface to the core of the equatorial undercurrent, where it can be distributed toward the entire global circulation. And that's been shown by some other studies that this region really gives rise to buoyancy that feeds the global ocean circulation. Okay, so then for completeness, there's another source of heat in this region, which is solar penetration. So this is the tropical Pacific, so it's really warm. There's lots of solar penetration, which also deposits heat. So it kind of opposes the vertical mixing, which takes the heat that's been kind of deposited by the solar penetration down into the ocean. And so if you combine the divergence of the turbulent heat flux and the solar, oh yeah, look, sorry, I missed this. This should say solar here, but anyway, the yellow is solar. If you combine those two profiles, you get the diabatic upwelling profile. And diabatic upwelling means that you have now looked at a parcel that has had some heat deposited into it, which means it has crossed an isotherm. So I call this the cross isothermal velocity or diabatic upwelling. Those are equivalent terms. So, and when we are in the thermocline, this is analogous to the vertical velocity upwelling because the isotherms are horizontal. So a cross isothermal motion would move the parcel up in the water column. Okay, so we've done some analysis based on 10-kilometer resolution forest ocean only simulations that are validated and explained more in these papers. And so this is the theoretical sort of curve of the diabatic upwelling that we've just derived from consideration. And then you can see this is the calculated diabatic upwelling, so that matches really well. And here is the total vertical velocity at this point on the equator. So you can see that roughly this diabatic upwelling is a third of the total vertical velocity. So this framework links the Pacific upwelling and mixing together because it shows how mixing contributes to upwelling in this region. And so here's a picture of both of them comparing the diabatic upwelling. So this will be the blue line and below will be the orange line here on the same color bar. So you can see that the diabetic upwelling is weaker, but we've seen from the profile that it's still a third is still a significant contribution to the total upwelling. And you can see sort of how it sits. So the diabetic upwelling, I usually show this in temperature coordinates because it's a movement across a temperature. So if you show it in depth coordinates, you would be sort of moving the signal with the moving of the isotherms. So it's a bit of a clearer view, but you can see the isotherms here. So if we just look at the 24 degrees Celsius isotherm in the upper picture, there's this line that indicates it. And then there's the 24 degrees Celsius isotherm here in the lower picture in gray. So you can see that sort of the core of the total upwelling is where the diabetic upwelling is sort of starting to kick in the water column. So it's really just depositing heat to below the 24 degrees Celsius isotherm into the thermocline. So then again, we've looked at scales, if we've been interested in scales. So we wanted to know what is the variability of this process on the different scales, temporal and spatial scales, those are connected. So for the El Niño Southern Oscillation, you can see clearly more diabetic upwelling during La Niña than during El Niño. And you can also split this variability into the seasonal cycle and into a subseasonal cycle, which is these tropical instability vortices. And you can see that there's a significant modulation of diabetic upwelling along all of these time scales. And then in the study, in the paper that I'm studying here, I've shown that the El Niño Southern Oscillation modulation is mainly dominated by the impact of stronger or less strong vertical mixing, which is related to the current shear. And during El Niño, we have less current shear, so less vertical mixing, et cetera, et cetera. Well, the seasonal cycle in the colder waters, it's also the current shear and the variability of the current shear and vertical mixing that contributes to the variability. And then up in the upper water column, you have a significant contribution of solar penetration to the variability. And on tropical instability wave timescales, it's also vertical mixing. So vertical mixing is sort of a main player here at all timescales. And there's also eddy covariance because again, the diabetic upwelling depends on a movement of a parcel across an isotherm, and with these tropical instability waves, you modify velocity shear, and isotherm movement. So this sort of co-varying of these factors gives also rise to more diabetic upwelling during high tropical instability wave kinetic energy occurrences. So now we're getting sort of into the territory of things that I've tried to do in the last couple of years, and I haven't quite finished yet. So I'm just showing some beginning results that I'm planning on diving into further. So I used the same POP forced ocean model simulation that has a number of La Niñas and 7 El Niños, and I wanted to see, okay, what happens when we consider ENSO diversity? Because ENSO is not always the same, right? ENSO can vary. You get the Central Pacific El Niño, where you get a warming, usually a weaker warming, more in the Central Pacific or western part of the Pacific, and you get the Eastern Pacific El Niño, where you have really strong warming, usually also connected to coastal warming here, which usually is the stronger of the two signals. So we do capture this variability with our POP output, and I just wanted to make a preliminary figure of what does this mean for WCI, for my diabetic upwelling. And so in contrast, you still have the C-sub temperature anomaly, and in colors, you now have the diabetic upwelling. And I think something you can see is that whenever you have an Eastern Pacific El Niño, so when there's like this whole warming of the equatorial Pacific toward all the way to the east, you're basically shutting down diabetic upwelling altogether. But when you have a Central Pacific El Niño, like for example here, where you get the main warming west of 140 west, this line is 140 west, then you still have diabetic upwelling happening, which would still be depositing heat from the surface down into the ocean. So you could think potentially of this as a feedback on this mode of El Niño, this specific manifestation of El Niño. But this is all I have to say on it so far, so that's to be explored. I'm also using this analysis to return to the other ocean. So now again, looking across the equator here in the Pacific at this diabetic upwelling signal, which is again strongest on the equator in the thermocline, where the heat is being taken up into the ocean. I was curious to see, okay, what happens in the Atlantic, where we also have an equatorial undercurrent, albeit weaker. Do we have a similar picture there? And it kind of depends on where we're looking at them. These are different color bars, by the way, so it's not stronger, it's actually weaker than this one. But we do see maybe shallower, but also contribution of diabetic upwelling here in the tropical Atlantic. And we can compare the along equatorial cross-section of the Pacific to the Atlantic. You can see some notable differences. In the Pacific, it seems to be kind of getting stronger as we go to the east, which is probably related to the fact that I did this wrong. That the equatorial undercurrent is actually stronger in the east in the Pacific than in the Atlantic. In the Atlantic, we also have this region of diabetic upwelling below, which could be from there's other currents that are sort of along the coast of Brazil, deeper here, that again I haven't explored yet, that give rise to heat exchange in the tropical Atlantic. So that was the diabetic upwelling. So I wanted to compare what does the total upwelling look like in the Pacific against the Atlantic. And again, you can see really analogous, the Pacific upwelling is the strongest on the equator across or a little bit, in the top of the thermocline further east around 140 West, which is everyone's favorite location who looks at Eastern Tropical Pacific processes. I say everyone very freely here. And then you can see that the Atlantic, everything is kind of, moved towards the west, which is really interesting because, again, upwelling is supposed to play a really big part in this Bjerknes feedback, connecting the subsurface to the surface. And when we look at the tropical Atlantic Niño, it's also sort of here. It's not here, right? So we have a more clear indication of these processes in the Pacific underlying the areas where we identify the variability of these zonal modes than in the Atlantic. So I think that's something to look into further. And then this is where what I just said, that you can see in contrast here, the equatorial undercurrents and the white contours. So in the Pacific, you can see it's stronger. So the strongest contour that I'm drawing here is 1.1 meter per second, and the Atlantic is 0.7, so it's weaker. The current shear is maybe approximately similar though, because these contours are spaced at 0.2 meter per second. So the current shear is still similar. And then I've also overlain the vertical mixing induced turbulent heat flux in colors for the Pacific and the Atlantic. And again, this is kind of interesting where we see this really strong uptake of heat here in the Pacific, in the Eastern Pacific cold tongue region, that is less strong, but also really less pronounced, less fixed to a location in the tropical Atlantic than it is in the Pacific. So I think given the connection of this diabetic upwelling to total upwelling to sea surface temperature variability, and this idea that the Bjerknes feedback kind of, works similar or works the same in both of these basins, we have some really, to the tropical observer eye, strong differences in the ocean basin. So I think this warrants some more exploration into which processes play a dominant role here. Okay, so that gets me kind of back to model biases, because all of these studies that I've looked at now are based on models, and sort of even coming here, my my aim was to find out more about model biases and improve them and get the process representation of these right. So there's a question then about how you compare a model to the real world, right? So usually when, I think this is something we're doing right now, we're kind of, looking at how does our model perform in terms of sea surface temperature and some dominant markers that are relevant to the global circulation, the climate. But then really in between the sea surface temperature manifestation in the real world and in the model, there's this host of processes that again are related in this case to this is the equatorial circulation, again with the thermocline, and then I put here the Walker circulation on top to show that these are coupled. And so something that I'm interested in is not only comparing the resulting variables such as sea surface temperature, but also the process and how it's represented. And this is sort of going back to my wanting to understand better how mixing parameterizations work and how mixing parameterizations could be improved. And so if we use some kind of unique ocean observations to compare directly the mixing representation in the real world. So this is turbulent heat flux from mixing measured by Jim Moon at 140 West, again, our favorite location. And this is the mixing taken from POP. And I don't have MOM right here, but it's the same bias. Basically, the vertical mixing induced turbulent heat flux taking up heat into the ocean is stronger than as we represented from the KPP. And this is another thing that I, came up against, is that me not knowing and thinking I really understood TKE, so I was really well poised to make an advance on mixing parameterization and coming here and everyone is KPP. Not to learn that again, but that's okay. So it might actually be interesting in comparing TKE to KPP. But again, another future thing. So you can see that if you do have this direct comparison, you can see that the turbulent heat flux induced by vertical mixing is overestimated in our climate models compared to observations. This is coinciding with a cold season temperature bias on the in the turbulent Pacific in the models compared to the real world. And so you can then dive in and look at, and this is now a forced ocean simulation, so the sea surface temperature here looks better than it would in a coupled simulation because the surface is more constrained. You can look at this in a process sense again. So the blue line is vertical mixing and surface cooling induced by this vertical mixing from observations throughout the seasonal cycle. And you can see that we have strong cooling here when the sea surface temperature falls, less cooling than surface heating indicated in red when the sea surface temperature rises in the beginning of the seasonal cycle. So this figure kind of implies that vertical mixing is a really important control on the sea surface temperature variability in the tropical Pacific. And if we compare this process representation in POP, again, to be repeated with MOM, but probably going to be similar, you can see that we really overestimate the cooling induced by our parameterized vertical mixing. And so the balance between the two, the heating and the cooling, is wrong. And yeah, in this case, it doesn't result in such a big sea surface temperature bias because, again, it's a forced ocean simulation. It's not as free. But in the coupled one, it will result in a cold sea surface temperature. So that was sort of a direct comparison of the mixing measurements that we don't have available everywhere. And so now thinking about KPP, which parameterizes vertical mixing in POP and will also parameterize it in MOM, in the INCA version of MOM, we can think about what are the ingredients that we put into KPP to create this vertical mixing. So that's kind of one step back from the direct process measurements, but you're still measuring things that go into the mixing parameterization. So it's still a more direct comparison than just comparing sea surface temperature and sea surface temperature. And the things that are relevant for modifying mixing in KPP are shear, so n square, and no, shear s squared, and stratification n squared. The golden ratio there is 0.25, at which point when the shear is 4 times as strong as the stratification, we get turbulent mixing. That's sort of an empirically known number. And so if we look at this, the distribution of where our data from tau, so from our 10140 mooring observation, sits along this s square n square space, you can see some clear modifications. So when we have, generally it sits around 0.25, which means that this area is marginally unstable. So it's really prone to mixing, which I've said this about 20 times now, but this just, we see this again. And the other thing that we see is that there's a clear change between whether we're in a cold phase, so La Nina, or a warm phase, where we should sit on higher shears here during La Nina. And so we can now look at, do we simulate the right shears and the right stratifications that we put into our mixing parameterizations to get the right amount of. So you have to be careful here with this comparison. It has to be along the same time scale. So this is hourly mooring data and hourly model data. And then this has also been interpolated or extrapolated to just have the same vertical resolution, because you cannot expect a model that has a coarser resolution to do the exact same as the really high resolution ocean. We also kind of expect this different tilt that's not along the 0.25 line, and that's because in our model, the point of mixing starts at 0.8 Richardson number, so ratio of shear to stratification. So that's also kind of okay and to be expected. But really, a difference that we see here are these low shears and low stratifications that are not present in the real world. And so now this is work that Deepak and I have done together, and in conjunction also with Dan Witt, who's done some LES analysis of vertical mixing and what contributes to vertical mixing. And he's then provided us with some ideas on how to change some parameters in the KPP mixing scheme. So now we have this model adjusted, where we can see that we've eliminated a large amount of this vertical shear, a low shear. So you could say the model is improved. You can also say that there is still some work to be done. But this is maybe a metric that is useful for looking at how are we getting the ingredients for our processes right, rather than just the resulting quantities. Okay, so this was the model bias. Another part of looking at model biases is a continuation of upwelling studies that I started and haven't fully explored yet. So basically, it's really hard to get to equatorial upwelling from just satellite data. There's cloudiness that gets in the way, so we can't really very well measure the surface winds that would drive our upwelling through divergence. So something that we have started and I have run but not yet analyzed fully is a reconstruction of winds from a Bayesian hierarchical model that combines observations, quick squares observations whenever they are available, with ERA5, which is a more which is spatially and temporally available everywhere, but then we make a correction with the observations from satellite to get an improved wind stress. And then you can use this improved wind stress product to estimate the Ekman-driven divergence, so the upwelling on the equator on a large scale that's driven by Ekman. And so this is something that, okay, this is to be listed. So because I haven't analyzed this yet, I don't have the absolute distribution of realistic upwelling driven from these Bayesian hierarchical model derived wind stresses. But something that I would like to tie this to is a regional ocean state estimate. So that means that someone has been improving the forcing of the ocean data and some parameters in the ocean model to get to a better representation of the ocean state. And so one of the things that they change is the wind stress. So I'm interested in comparing how does this wind stress that they have changed, and that's what I've calculated here, is Ekman divergence from the wind stresses in this state estimate. Once in the original, so ERA, that was ERA interim, that was the forcing data of this original state estimate, and then in the adjusted, so that's what they say they needed to change to get to the better representation of the ocean model. And you can see here, this is for the entire tropical equatorial Pacific, this is for the Western Pacific, for the Eastern Pacific, and you can see that in any case, the orange distribution, which is this adjusted distribution, has been pushed towards stronger wind-driven upwelling. Now, the thing that's missing and that I will add in here is the distribution of the Bayesian hierarchical model implied wind stresses to be continued. Okay, so that's sort of already kind of my future plans. You've heard some things that I'm looking at and that I'm interested in pursuing further. And something else that I have, I think, chewed everyone's ear off in the past is this TPOS Equatorial Pacific Experiment field campaign that's coming up that is now resulting out of these pre-field campaign studies that have lured me here in the beginning. So we have been refining a strategy of how to measure these Pacific upwelling and mixing processes for the TPEX-E, so equatorial eastern sort of equatorial part of this campaign. And there's a central Pacific campaign here also looking at air-sea coupling and processes in this region. That's something that I'm planning on staying heavily involved in. I'm really excited about because I think we will get measurements that will allow us to have more direct comparison of our model processes in the real world. This water mass transformation framework can be applied to BGC framework tracers and other tracers than heat. This is something that I've been wanting to do, but not really had the time yet. And related to BGC, Kristen and actually Elizabeth Maroon at Wisconsin, we have submitted a proposal to NOAA that even though I will not be here, I would continue to work on if it got funded. So those are some future plans, or like trying to stay involved with this community, with the efforts that I've already worked on. And I also wanted to show you my very near future plans, which involve a road trip across the Pacific Northwest that I'm super excited about, with lots of camping and driving around and hiking before I then fly out to Liverpool. So thank you very much. I hope we can keep in touch. And yeah, that's me.
Okay, seems like we have a few hands online, but we'll see if we have any questions in the room. Yes, no,
Yeah, just going back to one of your very first slides, you indicated that previous studies, when they looked at the correlations of the SST or upper ocean temperatures and the wind, they primarily sort of moved to like June, July framework, yet your analysis was showing May. Well, I'm trying to understand what the differences were between what you did and what the previous sort of accepted knowledge. Is it because of the previous one just simply looked at seasonal averages?
I think that's it. Yeah. This is, I think, so the previous studies that I've looked at were aggregates over seasonal averages. Then also I looked at ERA interim. So, and I mean, this was like a while ago. So it was the first time that someone looked at ERA interim. So that's also a different reanalysis product that I used compared to what people had used before and what they have built their averages on. I don't know if people at that time looked at the seasonal cycle and then decided, oh, June, July, August is the strongest and maybe ERA interim shows something different. Not entirely sure that's super believable because we wouldn't think that there would be such a big difference. But I think the main difference must be because of the seasonal aggregates.
Okay. Maureen, do you want to unmute yourself and ask the question? Okay. Maybe
I'm
that's
sorry. I thought
oh yeah, go ahead.
I was uploading, but I raised my hand.
Oh, can I
But
hear
sorry.
you?
Oh, maybe we turned down the volume.
Yeah. Oh, right. Sorry.
Try again.
Yeah, try again.
I'm sorry. I thought I was uploading, but I guess I just raised my hand. I'm sorry.
Yeah. Okay. Yeah. We'll miss you much, Anna. So this is from Simi. Thank you for your scientific contributions and expertise over the years, and best of luck in the UK. I think that's what everyone wants to say to you. Congratulations and wish you best of luck in the UK. Yeah. Okay. Go ahead. Greg.
Thinking about the model development cycle that we're deep into right now, and one of the things we often struggle with at this phase of development is getting an idea of how our ENSO looks in a new coupled model, because we typically, you have to run, the ENSO statistics are very non-stationary. You have to run really long simulations to get a stable statistic. I'm wondering if you have some thoughts on whether, rather than focusing on ENSO amplitude and period, if we focused on the strength of the Bjerknes feedback or pieces of the Bjerknes feedback, whether that statistic might stabilize more quickly than the ENSO amplitude itself.
There are changes in the strength of the Bjerknes feedback over different time periods. So I don't know if it will stabilize more quickly. But it's something we can look into, basically make a similar plot to, this, what I thought was a very sophisticated scatter plot of this multi-model reanalysis agreement and the strength of the correlation. So,
Yeah, I mean, if you did that for, 20-year segments from each of those runs, would they be all over the place or would they sort of cluster?
yeah, good question. I don't know I think in the last, let's say 70 years, there's at least three time periods that you can find that are somewhat different, but I don't know how statistically significant that difference is. There is talk about also people look at this in the future. How will the Bjerknes feedback develop in the future? How will it change its impact on tropical, Atlantic, and Pacific variability in the future? So I think I don't think we can expect that it's completely stationary as soon as we have 30 years. But how big those changes are in comparison to the other ENSO statistics, I don't know. And that might be worth looking into. Yeah.
Okay. One last question.
So what parameters did you change in KPP to improve the simulation?
Yeah, good question. There was what did we change? So we changed, I just recently talked to Bill about this. I would be lying if I said something now.
We're not used to that.
Yeah, but I don't want to do that. So there are some changes, again, sort of within observationally constrained rates.
Was it the Richardson number criterion or not?
Well, so when you say that, there's two parts where you can change it, right? So are you talking about 0.8 to something else? I think that's part of it, but then there's also another change that we did. So there's multiple, which is why this answer again kind of evades me right now.
Okay, so yeah, thank you so much, Anna. Best of luck.
Get squished in.
You're always on an airplane now.
Yeah, hopefully you can continue.
Definitely. I like
My standard trouble.
It's always like those.
Yeah. Thank you for showing up. Better than actually working. Yeah. So it's relevant. It's relevant. Yeah. Should we get lunch? Yeah, I'm gonna get lunch with us. I would love to. My director's doing a Q&A right now. Oh, shit. Okay.